Hi everyone, today we have Vincent and Laurence talking about their flow annealed important sampling bootstrap paper, freshly accepted by ICLR. And well, it's the first method to actually be able to sample from the Boltzmann distribution of a molecule uh, without molecular dynamics and actually faster than molecular dynamics. So let's have a look at that first real world useful Boltzmann generator.
Yeah, we start off with some introduction of basically the motivation of our work and some machine learning preliminaries that are needed to understand what we are doing. We'll then introduce our method, show some experimental results, and then go to the conclusion and also remaining questions in this field. All right. Molecules, they're not just static objects. They're in constant motion, of course, like the bonds vibrate. There are parts of the molecules which rotate with respect to each other. In statistical physics, we consider not just the single configurations, but we want to consider the distribution over all those configurations, all the possible configurations a molecule can assume, and the respective probabilities. And this distribution is called the Boltzmann distribution. And sampling from this Boltzmann distribution is a central challenge in statistical physics. Because it's very important, of course, in order to explore like which different configurations a molecule can assume, which possible transitions can happen. And also, most importantly, it is used to compute things like averages over those distributions, such as free energy differences, which are important for defining certain properties of molecules. So therefore, sampling from this Boltzmann distribution is very important. The challenging thing with Boltzmann distributions is that the unnormalized density is usually known. So, I mean, it can be obtained via physical modeling. It's not trivial, of course, to do this. However, like in our setting, we kind of assume the density is known, but sampling from this density is very hard. Usually, sampling is done through so-called molecular dynamic simulations, which would basically work as follows. You start with some initial configuration, then you would calculate the forces and then iteratively see how the molecular configurations transitions over time. But of course, the problem is that if you sample that way, then of course, like the MD samples within the time series, like then in the neighboring time points, like those samples, they will be very similar. So those the samples that you obtain with MD are highly correlated. And of course, in order to compute stuff like averages, you want to obtain something like independent samples from the Boltzmann distribution, ideally. So in order to solve this problem, in 2019, the idea of Boltzmann generators was introduced by the group of around Frank Noe at the University of Berlin. And the idea there is to approximate the Boltzmann distribution with a machine learning model, a so-called normalizing flow. I will explain on the next slide what the normalizing flow is, and then basically use it as a surrogate model. So instead of sampling from the Boltzmann distribution directly, we can just draw samples from the flow. And this can be done in one shot, as we also see, and we get independent samples in one shot, instead of doing very expensive molecular dynamics simulations. A nice thing is also that, as we will see, normalizing flows provide tractable density. So therefore, we can also do reweighting. I will also explain on a later slide what this is. And yes.
Maybe now to write, we're only training for a single, we only have a single protein here or a single molecule. And for that, we have access to some unnormalized density, so some energy function when we're training these models. And yeah, or I guess in the Boltzmann generator, they also have access to a few samples. But is this not the case that we have like tons of molecules and are training with many molecules as one might imagine as having in a data set. We kind of have no data set here at all, I guess.
Yeah, this is a good point. I mean, actually both is possible. I mean, the context that we are considering is exactly the one you described in the beginning, that we have one fixed molecule for which we want to describe the Boltzmann distribution, and then we train one model in order to model it. And I mean, this is already a challenging task. However, of course, you could also consider something like a conditional model where you basically you plug in the molecular graph or something like this, and you get then the Boltzmann distribution. I mean, something like this would, of course, be even more powerful, but this is a much more challenging problem. I mean, there have been works on this. I mean, there's this a paper by your fellow PhD students, this torsional diffusion paper, where exactly something like this is attempted. But this is really, I mean, this was the first attempt. I mean, and they have some interesting results, but like as far as we can see it, still the results are much poorer than if you would train a single model on a single molecule. But of course, you know, this is something interesting to work on as well. However, yeah, in this setting, we consider one model for one molecule. Good, so let's continue. Yeah, the setting, of course, is also very interesting for machine learning folks in general, also if you're not interested in molecules at all, because it's very similar to other machine learning problems, such as knowledge distillation. I mean, maybe you guys have heard of WaveNet, which was like a very expensive autoregressive model to generate audio. And in order to make the sampling faster, they then trained the normalizing flow to approximate this this model. Or there could also be posterior inference, where basically you are given a density, but you cannot directly sample from it because, you know, it's unnormalized, and therefore you want to approximate it and then sample from it. So that's, yeah, why it's interesting to look into the Boltzmann generators in general as well. Okay, let's clarify some terminology here that I already used. So what is a normalizing flow? So for people that don't know, so let's consider we define a random variable z in the d-dimensional space, which follows some distribution, which is usually a simple distribution such as a Gaussian, and this is called the base distribution. Let's further assume that we have a bijective and differentiable mapping f. And if we then apply this mapping to our random variable z, then we will obtain a new random variable x. And the distribution of this random variable x can be computed by the so-called change of variables formula, which is given on the slide. And here, this term jf is the Jacobian matrix of our bijective mapping, which is basically the matrix of the derivative with respect to all the components. And since, of course, f can be a very complex map, which could be also parameterized by some parameters or even by neural networks, of course, we can more or less express any distribution that we want with this approach. And of course, if we can do that, then we can also try to approximate a target distribution P of x with our flow model, a Q of x. This, yes.
Kind of the J can be pretty hard to compute.
Exactly. So yeah, for normalizing flows, typically people design them in such a way that this Jacobian, typically computing the Jacobian might not be a problem, but computing the determinant then is a problem. And you might also want to design your flow in such a way that this determinant is easy to compute and might not even require computing the entire Jacobian matrix. And yeah, there's some tricks to do that. Like on the next slide, I also will show one, but yeah, I mean, we are more or less, I mean, there are also other ways, basically trying approximations for the Jacobian determinant. I mean, we don't really want to go into details here because, you know, our model is, our work is more on like training flows, and like this training algorithm is more or less generic with respect to the exact flow architecture. All right, so F can be, this bijective mapping can of course be composed of several invertible and differentiable mappings. And then of course, if we compose them, the composed map is also invertible and differentiable. So we can build normalizing flows out of layers, similar to neural networks. And yeah, I mean, there are many common flow architectures. As I said, they use kind of different tricks in order to make the Jacobian determinant easy to compute. I listed a few of them here. And something I also want to highlight, there are also some special architectures which are able to learn distribution on complex geometries. So for instance, tori, spheres, or other geometries. One flow architecture that we use a lot in particular is the so-called neo-spline flow, which uses usually rational quadratic, of course could also be another kind of spline, with the parameters of the spline being computed by a neural network. So on the right side of the slide, you see basically, so spline consists of a set of knots, and basically the spline connects those knots in some kind of smooth way that also the derivative is kept continuous. And if we restrict this spline in such a way that the derivative is always positive, then of course, I mean, you have a strictly increasing function, which is invertible, which is then a function you can use in order to construct a flow. And such a spline is then applied element-wise to the random variable you want to map. And you can then realize such a new spline flow in an autoregressive fashion. I don't want to go into details here because it's not really what we're doing. But the thing we are doing is we realize that we are coupling layers, where basically you first leave a share of the random variable unchanged, and then the remaining random variables are element-wise mapped by spline, where the spline parameters are computed by a neural network. And the neural network is conditioned by the other half, so the previous half of the coordinates. This, of course, allows us to model very complex distributions, right? Because, I mean, the neural network can be arbitrarily complex, so therefore the parameters can take any values. I mean, obviously, we are not modifying half of our coordinates, but on the other side, we can also just after one layer then change the role of those two coordinates and thereby modify all the coordinates and get a very, very expressive transformation. And the nice thing about this new spline flow, which is why we are also using it, that it can also be restricted to work on different manifolds, such as with circular coordinates, as you would find them, for instance, on tori or also the cylinder surface. All right, so I explained now what normalizing flows are about, but how do we actually train them if you want to approximate a target distribution? There are different ways to do so. One problem setting could be that you have access to independent samples from your target distribution. Then you can train your flow by maximizing the expected log likelihood of your model. So basically, you just want to compute the expectation of your model, of your log probability of the model under the target distribution. And, since you have samples from a target distribution, you can just, estimate this with those samples. And yeah, this approach is equivalent to also minimizing the forward care divergence, which takes this form. If you estimate it using samples from the target distribution, I mean, this just as a side remark, I mean, there's just an additional term which drops out because it only contains the target distribution. And this is like a very popular approach to train normalizing flows, also to train other machine learning models. But the problem, of course, is independent samples for the target distribution might not always be available or expensive to generate. And I mean, as I talked in the said in the beginning, for instance, if you want to learn the Boltzmann distributions, this is exactly the case. I mean, there are ways to generate samples, but they're expensive to generate, especially if you want independent samples. You have to run very long MB simulations in order to generate those samples and to really get proper decorrelation there. Another approach to train normalizing flows is that if you just are given the unnormalized density of your target, you can also train them by minimizing the reverse scale divergence. So basically, you change the ordering of Q and P here in the KL divergence, which causes that you end up with an expectation over Q and not an expectation over P. And of course, expectations over Q can be estimated with samples from Q. And so Q is our normalizing flow. And from this flow, we can sample very efficiently, right? I mean, basically sampling just consists of sampling initially from the base distribution and then propagating those samples through our flow layers. And this is how we get a batch of independent samples. However, the problem of this approach on the other side is that the reverse scale divergence is mode seeking. So this will mean that our flow will only fit a subset of the modes that are present in the distribution. I also illustrate.
Why is this the case? The mode seekingness.
That's a good question. I think so. Basically, if you so imagine looking at this objective, if you have a batch of so consider, let's maybe consider this figure first. So basically, we have here a marginal distribution of our of a Boltzmann distribution of a molecule. You see there so there's basically a marginal distribution over those two angles. You see like in yellow and light green, those are like the modes. And basically where dark blue areas and white areas is basically where the density is very low. So, and if initially your model is initialized in such a way that it doesn't cover the entire distribution, then of course the samples from the flow, which you use in order to estimate this objective, they will basically, they will have like, I mean, the log probability for a target will be very high, of course. So if you cover this, for instance, this mode, and therefore, I mean, they are very happy there. So therefore, the training algorithm will force the flow to cover this mode even better. And on the other side, of course, there's also this entropy term here, which is supposed to cancel this off. But I mean, once you're in a state that only one mode is covered, then basically the entropy is just increased as much as that it covers the single mode, but it doesn't really, you will never get any samples at other modes, which would cause the flow to change in such a way to also cover this other mode. Does this roughly make sense?
Yeah. Oh, could you also lose some words on the why don't we need the normalized density of the target distribution here for this objective?
Oh yeah, this is true. I mean, yeah, I've written this on the slide. Yeah. So basically, just the point is, I mean, if P would be unnormalized, then of course, I mean, if you consider this objective, you know, you have some additional normalization constant as a factor in front of P, right? But then if you apply the logarithm, this of course can be turned into a sum. And in the end, in order to do training, we're only interested in like computing the gradients of our objective, which are then used in order to improve our flow step by step. But of course, if you compute the gradients of the constants, it's going to be zero. So the normalization constant doesn't have an influence on this, on the gradients of this objective. So therefore, yeah, it's fine to have an unnormalized objective here.
So then let's say we have the objective is no longer log of Q over P, but just the expectation of Q over P. Then how does that change things without the log?
So then it would scale the gradient by a constant. And things like Atom don't care about scaling the gradient by a constant because they just care about the direction of the gradient. So then that's also fine.
Yeah. and maybe that's interesting later.
Yeah, indeed. Yes.
Okay.
Good. Yeah. Okay. So yeah, this to the reverse scale divergence. Of course, there are also other objectives you could try to maximize or minimize, which are mask covering, so which do not have this problem of the that I just illustrated of the reverse scale divergence. Examples include the alpha divergence, which we will explain in more details later for certain values of alpha. One example is also the forward scale divergence, which is also a special case of the alpha divergence, as we see later. And yeah, I mean, those objectives, they can also be estimated with samples from the flow, but there the problem is that the variance of the objective is typically very high, and therefore training is very unstable. So for instance, we like for this setting here, this molecule, we also try this out, but I mean, I cannot show you any results just because the variance is so high that after one iteration, more or less all the parameters go to none, and so therefore you didn't learn anything. This is how bad it is.
Wait. Why are we talking also about training with samples here?
I mean, it's training with samples from the flow. I mean, you always need some kind of samples. You estimate your objective. I mean, typically you have some objective which contains some kind of expectation, right? It needs to be estimated. If you cannot compute it analytically, which is usually the case, you do it with samples. But the question is, do you do it with samples from your target or do it with samples from your model? And here we basically we would say, you know, we would like to do it with samples from our model, but then the variance is too high to allow training.
And if I do it with samples from the model and the forward KL divergence, then I need to reweight with basically the important sampling weights between the model distribution and the unnormalized target distribution.
Exactly, yeah. So you could, exactly. You could do forward KL divergence minimization. I mean, as I said, earlier, this can be done with samples from the target, but can also be done with samples from the flow. But then you basically do important sampling, which is a nice keyword because that's exactly what I wanted to mention next to for those who don't know what important sampling is. So assume we basically have some target distribution P, and we want to estimate an expectation of some function H over this distribution P, but we are unable to sample from P. That is, for instance, our Boltzmann distribution. We can do this, computing this expectation by using another distribution Q, and then use the following trick. So we basically would like to estimate this expectation here, which basically can be written out as an integral. And then we just include this factor 1 here, Q over Q. So Q will cancel out, but we will write it in this way, that we basically write it as an integral over Q of x. And then in addition to H of x, we have this additional term P over Q, which we will call our importance weight. So we can then thereby rephrase our expectation over P as an expectation over Q of this objective Hx times the importance weight. And then, of course, this expectation can be estimated with samples from Q. And here basically we just need to make sure the importance weights are normalized to get the right integral. And of course, in this situation, ideally we want a Q which is as close to P x times the absolute value of H of x in order to get a better estimate, right? I mean, if you're just sampling Q at points where the density, like P of our target, is very low and H of x doesn't have a significant value, then of course it's not of use. You want to have samples there where actually the major contribution to the expectation is happening. Okay, that's about important sampling. So the next section would be the method section. Are there any more questions regarding the things I talked about so far? Anything in the chat, maybe?
Nope.
Okay, if not, Laurence will take over for the next.
Yeah, Vincent, could you carry on sharing screen?
Sure, yeah, I can then.
Now someone pointed out, is it relatively easy to compute the energy?
So actually computing the energy, I mean, whether it's relatively easy or not depends on the molecule. And typically, I mean, if you have like a large molecule, I mean, even for like smaller molecules, of course, computing their energy can be expensive. And I mean, this is exactly also the critical part here. I mean, what we want to avoid, of course, is evaluating the energy too often, right? Because I mean, if you do MD simulation, we have to evaluate the energy or forces. I mean, basically the cost is very similarly. But if you just want to use, I mean, this is a way to generate samples which you could use for training. But on the other side, we could also evaluate the density, which is also, you know, dependent on the energy. But of course, if you would just train using the density, we also need to evaluate the density, which also causes us to evaluate the density at some points, right? So actually, what we want to do is not really, you know, just not using any MD samples, but what we actually want to do is minimizing the number of energy elevations that we have to do, right? Exactly because, like, for certain systems, certain molecular systems, evaluating this energy can be costly. So therefore, we want to do it as infrequently as possible.
Well, in the end, what you really want is to like the time that it takes to train your normalizing flow is not only dependent on the number of energy evaluations anymore.
Exactly. So it's also, I mean, it's also the number of flow evaluations, right? But typically the energy elevations, this is like the expensive thing. So this is what we want to minimize more. But of course, you know, if they have to use like orders of magnitude more flow evaluations, this is also not in our interest. So therefore, ideally, so what we consider in our paper is more or less, so keeping flow evaluations roughly equal, can we minimize the number of energy elevations? And then, of course, this will minimize will decrease the cost of training as much as possible.
Mm-hmm. Great, thank you.
Cool. Cool. So I'm just going to go through the method now, and we have quite a few ingredients. So I'm just going to go through them kind of one by one until we have all the puzzle pieces we need. And the first is just to think about what objective we actually want to minimize. And as Vincent mentioned previously, reverse scale divergence has this problem of being mode seeking, where it typically finds a subset of the modes and then fits them really well. And what we're interested is covering the whole distribution. So if our Boltzmann distribution has 100 modes, we would like our flow to have mass on all of these modes. So what we want is mass covering. And alpha divergence gives us a really nice way to express what we want. And it has this parameter alpha that just controls the degree to which the divergence measure is mode seeking versus mass covering, specifically with higher alpha. So alpha greater than 1, it becomes more mass covering. So that's shown in this plot here. So alpha divergence is equal to 0 for all alphas when P is exactly equal to Q. But what this plot shows is if P is a bimodal distribution and Q is Gaussian, then which Q minimizes the alpha divergence. And what you can see is that with low alpha divergence, Q is fitting one mode really well. And with high alpha divergence, Q is trying to cover the whole distribution. And the specific choice of alpha that we use is alpha equals 2. And so this is the next slide. And this is like a nice principal choice because it corresponds to minimizing the variance in the variance in the important sampling weights if we used Q as an important sampling distribution to estimate expectations over P. So this is the objective that we choose. And immediately we have a problem with this objective, which is it's very high variance if we try estimate it with samples from Q, which is kind of the standard approach one might take. And yeah, so if you go to the next slide, Vincent, so then the next problem is, how do we actually estimate this objective that we're interested in estimating? And you can see that it's going to be high variance over Q by just considering a case where P and Q are 1D Gaussian. So that's this figure on the right-hand side. And if you plot the integrand, which is in the green, what you see is the integrand is big in the regions where P is high and Q is low. So if you estimate that integrand with samples from Q, well, Q is not going to be placing samples in the important regions of our loss. So essentially, it's not going to be, we're not going to be able to train the flow with its own samples. And the optimal distribution, if we could sample from it for estimating this alpha divergence, would actually be P squared over Q. So if we sampled in proportion to the size of the integrand, however, the distribution is intractable, so we can't get samples from this either. And this is where annealed importance sampling comes in our method, which is we can actually use it to get samples. So we can combine our flow with annealed importance sampling to get samples approximately from this ideal distribution P squared over Q. And the way annealed importance sampling works is it begins by sampling from some proposal distribution. So in this case, that's our flow Q. And then it transitions via Markov chain Monte Carlo through a sequence of intermediate distributions towards some target distribution P of n. And then using those samples from the final stage of MCMC, you can estimate expectations with respect to P of n with the formula given at the bottom of the slide. So yeah, by the end of annealed importance sampling, what you have is the samples close to P of, not exactly from P of n, correct, to do importance sampling. And this has much lower variance than if you just naively estimated some expectation using samples directly from Q. So the kind of trick that we do is to sample from Q and then run annealed importance sampling with P squared over Q as the target for annealed importance sampling, to then give samples that are going to be really good for estimating our loss, which we use for training alpha. And specifically, we derive this.
Okay, so what you do is Laurence, oh no, sorry, not Laurence, Vincent already mentioned this thingy of training with the forward KL divergence, right? Let's maybe now not talk about the difference between KL and alpha divergence, but if we train with samples from the Boltzmann of our normalizing flow, and then with the forward KL divergence, so also just with an unnormalized density, and in the end we only need that, and then we do this reweighting with importance sampling, right? We take our samples and in the KL divergence we reweight with the importance sampling weights. But now what you're doing is basically not taking the samples that your normalizing flow produced. You're actually further changing them around a little bit with annealed importance sampling, and then also taking the weights, or like all of the importance weightings, or all of the transition weightings, or all of the importance sampling weights, because you now have multiple importance sampling steps, if you want to call that. You're accumulating all of them, and then in the end you're also still taking the one to the unnormalized density, and then these you're using these weights instead with your transformed samples.
Yep,
okay,
that's exactly right.
And now this is like sort of separate, right, from using the alpha divergence. Is that correct?
Yeah.
Okay.
Yeah.
So we could also do that for normal forward KL divergence training. Yeah. Have you also done that or tried experiments with that?
Yeah. So one thing that we did is we just varied the value of alpha, and alpha equals 1 is equal to the forward KL. Okay. And again, that's a lot better than if you train using the standard way of using reverse KL divergence. So it still helps a lot, but it does worse than alpha equals 2 in terms of effective sample size. yeah, but that is something that you can do, and it does work. Yeah.
Okay, cool. But now we have this procedure. We go get our samples from normalizing flow. We change the samples further with annealed importance sampling while keeping track of all the importance weight updates, and then we have this objective here.
Yeah, so this objective is for the alpha equals 2 divergence. Actually, I'm not going to go through the derivation because it's a bit long, but yeah, I have two versions of the derivation. There's the one like in the main section of the paper, and then where we actually assume P is normalized, and then we have another version where we also like keep track of the normalizing constant in the appendix. And yeah, if anyone wants to look at that for further details. But yeah, so the key idea here is that annealed importance sampling is giving us these samples that are of much higher quality for training the flow than if we just use the samples from the flow. And then, yeah, so the reason that we call it a bootstrap is that the start of annealed importance sampling is using the samples from the flow. So we're kind of improving the samples and then using that to update the flow. And that recurs where at each state, the base distribution of our annealed importance sampling is going to get better, which is then going to help us find the important regions in the target to update our flow with, and then we're going to update the flow again. So that gives us kind of like what the base key part of the flow annealed importance sampling bootstrap. And if you go to the next slide, Vincent, one thing that we can do is look at the signal to noise ratio of the gradients we get with our method. So in this case, we can set P and Q both to Gaussians. So we can actually just sample directly from P if we want to in this case. And we can then compare the signal to noise ratio of various estimators for estimating this alpha equals 2 divergence loss. So what we do is we estimate it with samples from Q. So that's the dark dotted line.
Sorry.
And yeah.
Can you first explain what signal to noise ratio is?
Yeah, so it's going to be the empirical mean of the gradient so that's going to be the signal divided by the standard deviation of the gradient, which is the noise. So what we're going to see is like given this fixed P and fixed Q, if we estimate the gradient with respect to, I think we're doing with respect to the mean of Q here, how noisy is that gradient? So how much does it vary around the mean? And we can actually calculate the analytical mean for what the gradient should be. So it's like a nice, easy toy problem for seeing how well our method compares. And what we see is that, yeah, so if you look at this middle figure B, that if you set the target of annealed importance sampling to P, then that already does, so that's just setting it to our target distribution. That already does a lot better than with samples from Q. And of course, if we have access to the ground truth, then that does even better than annealed importance sampling with P as the target, because that's essentially going to be annealed importance sampling with zero variance in the weights. It would be like if our annealed importance sampling was perfect. But then what we see is with this P squared over Q target, we can actually do even better than samples with P. And then on the furthest to the right-hand plot, what we see is as we increase the number of intermediate distributions in our annealed importance sampling procedure, the signal to noise ratio of our gradients just like carries on improving. And if P was our target, then the signal to noise ratio is actually approaching P. So it's becoming almost as good as if we could just sample directly from P. And if we use this optimal P squared over Q distribution, we can actually do a lot better even than with samples from P.
Yeah, can you
like almost more important is, yeah.
Can you maybe after you say what's almost more important, but can you then lose a few more words about this P squared over Q instead of P as a target, and why this is like the lowest variance estimator or something like that?
Yeah. Okay, so the thing that I was going to say before is actually like the thing that we care about more is actually that we're just doing way better than if we estimate the loss with samples from Q. So that's kind of the bottom line in these plots, and you can see that that is really, really noisy. And this is essentially why training with alpha equals 2 divergence with samples from Q just doesn't work. It's because the signal to noise ratio of the radiance is really bad. But yeah, so this P squared over Q target, Vincent, can you just go back, I think 2 slides? Or 3 slides, 4 slides? Yeah, okay, so our loss is this P squared over Q. And so that's this green curve. And we essentially estimating this integral with Monte Carlo. And so what you can see is to estimate this integral well, you want to place probability mass on the regions where the integrand of the integral is the biggest. And you can see P squared over Q is proportional to the integrand. So if you look at the red curve, you can see that it's actually more aligned with the green curve than P. And it's actually focusing on the regions where P is big and Q is low, which is why it's better than P, because P is not focusing on the regions where Q is low. So it's essentially going to take us for the regions where the target is big and our flow is not actually capturing the target well. And then that's what we're going to use to update the flow. Does that make sense?
So this is just because of the particular training target of alpha equals 2.
Yeah, I mean, so we can generalize the same principle. So for any integrand that's greater than 0, the optimal distribution for estimating it is going to be this distribution proportional to the integrand.
Okay, and then if I do my forward KL divergence with instead of important sampling with annealed important sampling, what target for the annealed important sampling should I then use?
So actually in our derivation, so if you set alpha equals 1, then what you actually get is that the optimal distribution would just be P. So then you end up just targeting P. And you can see kind of that's also like it kind of captures the mass covering versus mode seeking ability, where the higher the higher alpha is, the more Q is appearing in this denominator. So the more it's kind of focusing on the regions where Q is not meeting P. Does that make sense?
Yeah.
Yeah. Okay, so if we go.
By the way, the derivation of the optimal target for any alpha value for the alpha divergence is also in the appendix of our paper.
Yeah. Okay, so then we have one final ingredient to get to the actual method that we use in the paper.
Before you get to the final ingredient, sorry, but I'm not sure if you already mentioned what the bars mean in your objectives.
Yeah,
so
that actually means stop gradients there. So we're not back propagating through the annealed important sampling process. That's kind of like an extra thing that's actually interesting to think about. But yeah, in this paper, we just directly estimating the loss with them. We're not trying to differentiate through important sampling. So all the bars are stop gradients.
And why? Like, is it just computational, or does it have another motivation?
So I think there potentially would be ways of actually using the gradients through annealed important sampling. But I think there's like quite a lot of trade-offs to think about there, because it's like it's a long iterated system. So I think the gradients can get very chaotic. But there's like a set of new papers on differentiable annealed important sampling. I'm not aware of a method that works super well yet. It's like something we're interested in, but basically until there's a really good way of differentiating through annealed important sampling, we kind of avoided it because we thought it would make training worse. Yeah.
But especially say if you want to like tune some parameters of annealed important sampling, this of course could be beneficial as well. But yeah, I mean, as Laurence said, it's just very complicated, computationally expensive. So therefore we didn't do this, but you know, if somebody is very, very familiar with this, I mean, we would be very happy to follow up on that.
Yeah, I think it would be like a interesting extension, which would be another version of the objective that's also differentiating through annealed important sampling. And I think there's like quite a lot of trade-offs to assess there also, just with these the issues of differentiating through a like iterated system like annealed important sampling. Okay, so if we go, okay, so yeah, so the annealed important procedure is much more expensive than just sampling from a flow. So per kind of objective evaluation, we're having to do more compute to get these good samples. Specifically, like to run annealed importance sampling, we sample from the flow and then do, for each intermediate distribution, multiple flow and target evaluations. So it's kind of, it can be multiple factors more expensive per objective. And it can be worth it because the signal to noise ratio is just a lot better. But one thing that we add to our method is reusing these samples from annealed importance sampling throughout training. And the way that we can see how to do this is, so yeah, if we consider our original objective, instead of weighting by the importance weights, what we could instead do is to sample in proportion to the same importance weights, and then calculate our objective with that, and those two would be approximately equal. Yeah, in the second equation, you can ignore the nabblers. So yeah, we could just sample in proportion to the weights. But then what actually happens in training is we've run annealed importance sampling in the past, and that was run with previous values of the flow parameters. So we also have to correct for the fact that our p squared over q target had a different q in the denominator. So that's where we have this log correction factor, log W correction. So then what we can do is, as throughout our training, save the samples that we generate and then reuse them to update our flow with this W correction factor that accounts for the fact that they were generated with our old samples. And this actually lets us do multiple gradient updates on each sample that we generate with annealed importance sampling, which just improves the data efficiency of our training. Yeah, so that's all the ingredients we need. So now we can actually run through the overall algorithm. So it has, yeah, so in each iteration of training, what we're going to do is these kind of two separate things. The first is we're going to generate samples with annealed importance sampling. So we're going to sample from our flow. We're going to run annealed importance sampling with p squared over q as the target. And then we're going to add them to this thing that I call a replay buffer, which is just basically storing all of the samples of X, the corresponding importance weights. And we also need to save the log Q at that point in training so that we can do this correction later. So yeah, we have this generation step, and then for each generation step, we then sample from our buffer in proportion to the importance weight. We calculate the correction factor to account for the fact that our theta has been updated between when the original annealed importance sampling algorithm was run and the current date of training that we're at. And then we can estimate our loss. Yeah.
Why can't we sort of do these two things at the same time? Like, why do you always, why do you always first do your AIS and then you run your iteration or your training iteration? And can't we do the AIS stuff at the same time as training?
Yeah, so you could have like a completely asynchronous kind of AIS method to your updating your flow method, and they could be kind of communicating, and that would be a more efficient version. So yeah, this is written like to be sequential, not because it has to be, but just because it's a simpler way of looking at it. The like analogy that I normally think of for this is a replay buffer and reinforcement learning, if you're familiar with that. And then they completely do that. So the kind of generation of experience is completely decoupled to the updating of the parameters. Yeah, it can be done in parallel. Yeah, and then so then we update our parameters. We also have to we re-update the importance weights in the buffer according to the latest version of the parameters. So that's this line before the last. Yeah, and then we can perform gradient descent on theta. And what you can see here is we have for iteration 1 to L, so we're sampling from the buffer multiple times. So what that just means is that per sample generated by annealed importance sampling, we actually update our model multiple times off it. Yeah, and that's the whole algorithm. Are there any questions for that? Otherwise, I'll move on to some results.
No, makes sense to me.
Okay, cool. Cool. Yeah, so let's look at some results. So the first experiment we have is this mixture of Gaussians problem. So what we do is we just make up a target distribution that is a mixture of Gaussians in 2D. I think there's 40 mixture components. And what's really nice about this about this specific problem is we are in control of the target distribution, so we can sample from it directly. And we can also visualize it very easily because it's in 2D. And evaluation can actually be quite hard on the more complicated problems, where this one you can be like much confident. Yeah, and so we train a variety of models. We also, one other thing that we do is we give the flow a really bad initialization. You can see on the top left plot there, the initialization of the flow. And this just makes the problem like really hard. And it also like kind of tests the capacity of the method for discovering new modes that's not included initially in the flow. Yeah,
How
also
do how do you
yeah.
make sure that you have the initialization?
Yeah, so you can just initialize the flow to an identity transform and initialize the base distribution of the flow to a normal 0-1 Gaussian.
Okay.
Yeah, so then we train with a variety of methods. The first one is via maximum likelihood, and this is because we can just sample directly from the flow. And you can see this method does super well and captures all the modes in the target distribution. But this is kind of, we're actually not directly comparing our method to the method with maximum likelihood, because the whole thing we're trying to avoid is just taking tons of samples directly from the target distribution, because that's not possible in the case of the Boltzmann distribution. So then we have a variety of methods that aren't using these samples from maximum likelihood. And that is, so we have flow with KL divergence. So that's minimizing reverse KL divergence estimated with samples from the flow. And you can see that that just fits a subset of the modes in the target distribution. We have a flow with a resampling base distribution, which is basically a method that can improve the expressiveness of a flow, where you also have this kind of resampling step in the base distribution, but this similarly doesn't work. Then we have SNF and Craft, which are actually methods that combine flows with MCMC, but they also both use a reverse KL divergence style objective. And this leads them to also just capturing a subset of the modes. Yeah, and then we have our method, and we have it both with and without the replay buffer. And you can see it's working quite nicely. Specifically with the replay buffer, works pretty similarly to just if we train with maximum likelihood.
Yeah, but
so
here it's almost like, yeah. If you train without the replay buffer, right? This should be better. Am I wrong?
This is for a fixed number of target evaluations, and the replay buffer is going to then be doing like multiple flow updates per. So then it actually is more efficient, so it does better.
Okay.
Also, another thing is the resampling step in the replay buffer is actually quite helpful, because you then say you have 10,000 samples in your replay buffer, you actually grab the subset of the samples that contributed the most to p squared over q. So almost all of your samples are very useful, where just with when you use the samples immediately generated by Annealed importance sampling, what can still sometimes happen is some of the samples are a lot better than the other. So maybe only a fraction of your batch is kind of very useful, where when you use this replay buffer, kind of your whole batch is really useful. Yeah,
I would still be curious what what we actually want to see here. Like to me, it's not clear if the bottom right most or the fab without buffer or fab with buffer is what we would like to see, or which one looks better. And then maybe showing the same plot with the same amount of samples, but just drawn from the Gaussian mixture, would show us what we really would want to see, right?
So what do you mean by the same number of samples?
You have a certain number of samples that you show here in each plot.
Yeah,
and
so
now
that's the same
also,
for each plot.
yeah, and now you also draw the same number of samples from the ground truth Gaussian mixture and show the same plot. And then
Oh, I get what you mean. Instead of the contours.
like separately, of course, you show the contours, but another plot where you show the contours and the Gaussian mixture sum.
Yeah, I agree. That would be a good plot.
To me,
like
it's not so clear.
I mean, we also have quantitative evaluations in our paper. I think, unfortunately, we don't have them in those slides. Let me see. Oh, yeah. But we have, like, for the other experiment, for the Alanine dipeptide, which is a bit more interesting, we also have quantitative evaluations.
But let's maybe get to these experiments, I guess.
Awesome. Yeah. So then I'll explain a bit about this set of experiments. Yeah. So as I said, obviously we didn't just want to apply this to a mixture of Gaussians. I mean, it's interesting, for example, to roughly get feeling for whether the method is working or not, but we want to actually work, of course, with real world molecules. So, and here just illustrate a rough setup that we used. So we modeled the molecule with using internal coordinates, so not Cartesian coordinates. So on the right side of the slide, you can see illustration of the two coordinate times. So Cartesian coordinates would just be XYZ coordinates for all the atoms, while internal coordinates is a set of bond lengths, so the distances between the atoms, then also bond angles, so basically the angle between two bonds, and dihedral angles, which basically is the angle between a plane which is spanned by the atoms A, B, C, and B, C, D, so the angle between those planes. And those coordinates have the advantage that they are invariant with respect to translations or rotations, right? I mean, if you move this molecule, then the bond lengths and the angles, they won't change. Also, same with rotation. Some of those coordinates will be like periodic, like circular coordinates, obviously, which we need to treat in a proper way. I mean, I already mentioned earlier, I mean, this is like those kind of coordinates live on a special manifold, such as on a tori. So therefore we need a flow which can handle all those coordinates. And as I already mentioned in the beginning, we use this near spline flow because it has this advantage that it can treat periodic coordinates and like unrestricted coordinates at the same time. So both our angles.
Then when accounting for this periodicity, also account for, let's say we have a carbon with 3 hydrogens attached to it, then you don't just have the rotating 360-degree periodicity, but also the rotating 120 degrees periodicity.
So we didn't account for this. So basically, I mean the way we kind of get around this, I mean we kind of have like a fixed set of coordinates, right? So therefore the periodicity, it's so basically this needs to be learned by the flow. Right. So yeah, so I mean, sure, you could also do this, but then of course, incorporating, I mean, then there might be also other groups which satisfy certain symmetries and so forth, which makes everything more complicated. I mean, obviously this is something you can also do, but I mean, we just did the things I mentioned, but the rest the flow model has to figure out itself. But yeah, I mean, I agree that, say, if you want to scale this up to even larger systems, it might be helpful to incorporate more of those symmetries as well.
Yeah.
Good. One other important point that I want to mention is chirality actually becomes a problem when dealing with the kind of problems that we do. So alanine dipeptide, which is the molecule which we consider in our paper, comes in 2 chiral forms. So we can see here the L form and the D form. And the interesting part here is the part in the middle. So basically you see, I mean, there's this methyl group here, there's this hydrogen here. And for the L form, the methyl group is like pointing towards us, and the hydrogen atom pointing the other way. And with this other chiral form, it's exactly the opposite. And of course, the energy of those two configuration, it's like, except some it's like very small like possible deviations, is exactly the same. So therefore, if you would blindly train a model which basically starts from like random configuration, it would then learn to generate molecules which satisfy either of those two chiral forms. However, in nature, we only observe the L form and not the D form. I mean, the D form could theoretically be synthesized in the lab, but since in nature we only see the L form, we also want a model which only generates configuration for the L form. And the way we restricted our model to only generate those forms is that during training, we draw samples from our flow, and then we use some dihedral angles which are close to this chiral center, and then we restricted those the difference of two chiral angles to be in a certain interval, so that we can ensure that we only have the L form and not the D form. And basically all the samples which do not fall into this interval we discard, and all the other samples we use for training. And thereby we enforce the model earlier in the training to learn to only generate samples from those chiral configuration. Then very quickly the model will only generate samples in this chiral configuration. Of course, I mean, there are other ways to do this. You could also try to, for instance, explicitly restrict your coordinates in such a way that only the L form can occur. I mean, this is how we did it. And but yeah, I wanted to mention this because I mean, it's an interesting problem which doesn't occur in previous Boltzmann generator papers, because of course, if you have samples, then all the samples will come from one of the two chiral forms, like only the L form in this case. So therefore, you don't really have to consider this case. However, of course, if you want to train only using the unnormalized density, then you, I mean, a priori, the energy won't distinguish between those two chiral forms. I mean, of course, you could also add some biasing potentials there, but you can also, do some heuristic filtering as we did to force your model to only learn to generate one of those two forms. All right, let's get to some results. So, yeah, what typically people consider when working with proteins, they like an dipeptide, or those two dihedral angles, phi and psi, which are basically for longer protein change. They would also determine then whether like a protein locally falls into like an alpha helix or beta sheet or something else. And so this is why we look at those coordinates. And here on the right side of the slide, you see the marginal distribution of the angle phi, but you see the probability density not like in usual scale, but in log scale. And we do this in order to highlight, I mean, there's like a very dim mode here on the right side, roughly at pi divided by 4. And this mode is so dim that you couldn't even like really see it if you would plot the probability density with a normal scale. But we want to highlight it here because actually this mode, this is something which is challenging even to resolve for the flow, which is trained using samples, molecular dynamics samples, which is the blue curve here. And if you try to reweight this flow, you also see that, I mean, that completely fails to capture the shape of the function. So the green curve is very off in this setting, in this interval where the stim mode is. Then our model, which is fab with replay buffer, I mean, which is this red line. I mean, it already models the modes reasonably well, but you still see they're like it's slightly off at some places. But the nice thing is, I mean, as Laurence mentioned in the method section, the nice thing about using the α-divergence is also that it minimizes the variance of the importance rate. So it makes reweighting our samples even better, which is of course very interesting for us because in this Boltzmann generator setting, you typically want to do reweighting. And if we reweight our density here, you see like that it fits the target super well, even in those like very, very low probability density.
So to be clear, like, am I right that what we should be comparing here is the green line and the purple line? The other two kind of don't really make sense. There's no reason not to do the reweighting. Is that right?
I mean, there might be a reason not to do reweighting if the variance of your importance rates are too high. So for instance, in some of the Boltzmann generator papers, they train a flow on MD samples, but they cannot do reweighting just simply because the variance of the importance weights is too high, right? This is the case here, right? I mean, if you compare the blue and the green line looks worse than the blue line, right? So if you do, since the variance of the importance weight is so high, you're worse off doing reweighting than not doing it. While with our approach, you're better off, but this is only due to the fact that you use this particular objective which minimizes the variance of the importance weights, right? Yeah. But I mean, if the variance of the importance weight is high, you might be even worse off.
Interesting.
This is, I mean, I also have some numbers to illustrate this even further. Let's first also have a look at some Ramachandran plots. So those are plots basically showing the marginal distribution of those two angles, which I showed that alanine dipeptide. So I mean, here on the left, you see the ground truth, how it's supposed to look like. You see, I mean, for this flow, which is trained using the MD samples with maximum likelihood, you see, I mean, all the areas with like very high probability density, they are very well modeled, but in the area with the very low probability density, the model still struggles, and reweighting doesn't really help there, as we saw in the previous slide. Well, if you use our model, I mean, really, the model itself is already pretty good, but if you do reweighting, then it's more or less indistinguishable from the ground truth.
From the previous slide, we looked at a horizontal. At the previous slide, we looked at a horizontal slice through this thing, right? Where is the horizontal slice?
It's not exactly a slice, but it's basically if you would sum up the entire this dimension, right? I mean, it's a marginal, so therefore, if you would sum up the phi, the psi dimension, this is then what you would get, right? So basically, I mean, so this mode here, this corresponds basically to the sum of those two modes, right? And then also, I mean, you have those two modes here, but I mean, here they are like those four modes, right? There's a mode here, mode here, mode here, but it like always two of them sum up to those modes. Yeah, it's a bit, you know, we work in high dimensions here, so therefore it's always a bit tricky, but, you know, in order to visualize it and to get at least some kind of understanding, we try to plot those margins, right? I mean, actually, I mean, the actual system has like 60 coordinates. Of course, then, like, if you would have a look at the full distribution, it could be even more complicated, much more modes and all the coordinates, right?
Well, that's the nice thing about having two torsion angles in your model.
Yeah, exactly. But at least like the most important stuff is condensed in them.
We have the question in the chat how you got the ground truth.
Oh yeah, this is also ground truth. Yeah, it's of course. So the ground truth is still like generated using MD, as written also in the caption here. But this is like a very long MD. So basically, like our test set. So for the training set, we used, I think, like 1 million samples, where we also like generated a very, very long MD, and then I think took like every 100 sample or something like this. And the test set
only for the maximum likelihoods.
Only for maximum likelihood, exactly. So our method doesn't use them. And then the test set is even larger data. So it's like 10 million samples, and basically, you know,
did you run that yourself?
Yeah, we run it on our cluster ourselves. Yeah, and it's also, I mean, it's not just a simple sequential MD. It's also like using using this replica exchange idea in order to really cover the entire energy surface very well. Also did like multiple simulations in parallel with different starting seeds in order to really try to cover the entire distribution as well as possible, so that we can use it as a ground truth. But yeah, I mean, it was like super expensive. I think like in the paper we stated somewhere, I think it was like more than 100K CPU hours that we spent on this MD simulation, just for this relatively small system to get like ground truth and training data set and validation set.
How long does it take to train your flow?
So the flow can be trained in like, so depending on which method you use, obviously, but typically like 1 to 2 days. No, I think it's even faster. So we improved it even more. I think now it's less than a day. I think the FAB training took, I think, on alanine dipeptide, I think 15 or 16 hours. yeah, the exact numbers will be in the paper.
I think the MD is like a week or something.
Yeah.
Say again?
I think, and the MD was like a week that you ran it on the cluster or something.
Yeah. So just doing the MDs, yeah. I mean, training the flow is of course quicker, but of course, I mean, you know, if we train the flow using MD samples, of course we do the MD ahead of time. We could do it also asynchronously at the time. So therefore, basically, in order to consider the compute cost there, you need to add up the number of flow calculations that you add, number of flow evaluations that you used, and the number of target evaluations that you used. Although
But
this,
why do you here show the maximum likelihood training without reweighting?
Just because, I mean, the other with reweighting it would look worse. So therefore, we basically put the best looking plot here, which puts like our baseline, competing baseline, the most favorable light, because we thought that's like the first comparison.
Yeah.
So in the paper we have all the cases, also all the I mean, we have like there are several baselines we considered, which are shown in this table here. In our paper in the appendix, you have like all the Ramadan plots for all of them with and without reweighting. And yeah, let's talk some numbers here. So one very important metric that is typically considered, Laurence already briefly mentioned this. It is the so-called effective sample size. So roughly speaking, so the effect, if you draw a batch of samples and you compute the importance weights, then of course it could be the case that the importance weights are all basically the same. And in this case, of course, the effective sample size would be basically how many samples you draw, right? Because each of those samples in your batch contributes the same to your like estimate or whatever you do with the samples. But on the other side, say if like only like one sample has a very high importance weights and all the other samples have a very low importance weights, I mean, then effectively you're not using like all the samples in your batch if you would compute some expectation, right? But you would only essentially use this one sample. So then the effective sample size would be 1. So, and of course we can also compute this as a percentage. And then of course, ideally we want something like effective sample size of 100. But often the effective sample size is lower. And I mean, as I already mentioned, with the flow which is trained on the MD samples with maximum likelihood, it has a relatively low effective sample size, so only 2.8%, right? So this is why if we do the reweighting, actually the KL divergence goes down, as you can see in the table. Yeah, then of course we have like a bunch of other methods. We have like the training using the α-divergence, which produces like terrible results. As I said, I mean, since the variance is so high, basically it's not learning anything at all. We train the flow using the KL divergence. You know, a bunch of different methods. This recentrally-based distribution, stochastic normalizing flow. I mean, it's all trained using the KL, just like different flow architectures. You know, and some of them we have allegedly like high effective sample sizes. But the reason is only that we are fitting only a singular mode. And of course, you know, estimating this effective sample size becomes a bit difficult, right? Because I mean, within the mode, all the importance weights might be more or less the same. But of course, we are still missing other parts of distribution, which is reflected in a very high KL divergence, which is why, I mean, those are still not models that we want to use. But if you use our model, I mean, really the FAB method with replay buffer, there we have effective sample size of 92.8%, so very high. And also, I mean, there, if you do reweighting, the KL divergence drops even more. So this is really the ideal scenario that we want. And even the expected log likelihood of the model given samples from our test set is even higher than from the flow, which was trained with maximum likelihood. Yeah, I mean, this is already good. I mean, the numbers are better for our method. On the other side, of course, it could be to a price that it is more expensive to train it. And it turns out this is not the case. So here we show what I was already mentioning before. So basically the way we measure expense, like computation expense, is the number of flow evaluations, which we want to more or less ideally keep the same for all those methods. I mean, we made an exception for methods which are really very slow because they do like the stochastic normalizing flow, because it does some sampling in the middle. So therefore, just would have taken like many weeks to train it. I mean, we think we trained it for a week, so there, and this, which is already a lot, but still we couldn't do the same number of flow evaluations. And then the other important ingredient is number of target evaluations. I mean, this is the thing which was already asked before, like evaluating the energy, evaluating the forces, this is the expensive part. So this is the thing we want to minimize. And there we really see that if you train the flow using maximum likelihood based on MD samples, I mean, we have to generate those MD samples in the first place, and it takes roughly 100 times more target evaluations than if you train the flow using with our method using the replay buffer, right? I mean, here I have 2.3 times 10 to the power of 10, and here I have 2.0 times 10 to the power of 8. So 2 out of magnitudes difference.
Okay.
Yeah.
So for you, I think you said you take 1 million samples to train your maximum likelihood flow. Is that correct?
Yeah, exactly. Yeah.
Okay, so you take around 10,000 MD steps to obtain one decorrelated MD sample that you use for training, or is that wrong?
1,000,000
to 6, 10 to the 6, and then
so I think it's a bit, it's a bit more subtle than that. I think it's less than 10,000, but the thing is, we do this. I mean, so the actual system that we are considering is at 300 Kelvin, but the problem is at 300 Kelvin, if you run an MD simulation, then it's just extremely rare that we have to transition to this like rare mode, right? So therefore, we cannot just do that. I mean, then to get decorrelated samples, it would be even more expensive. So what we do is we do this replica exchange MD, where basically you have like the system at several temperatures, and we do like in periodic steps, we do like we exchange the state of those two systems of different temperatures. Like the highest system has something like temperature, I think, at 1000. There all the modes can be sampled like quite rapidly. Then we have like, I think, several steps in between. I think in steps of 50 or something like this. So we have like, I think 20 different replicas. And then of course, in each of those replicas, we need to evaluate the energies as well, right? I mean, all those things have to be done in parallel. Then I think we take like every thousands or less of one. Maybe I think, yeah, if it's like roughly every 1,000 sample, then it should work, right? I mean, it's roughly then 20 times 1,000, and then it should be like 20,000 times 1 million, and then this should be this number.
I'm still the last thing I'm wondering about is the comparison of the flow with wait a second. In the previous table, do you have the flow with forward KL divergence? Oh yeah, you have it, right? This is the no. I would be interested in the flow with forward KL divergence and annealed importance sampling to get the
yeah. This is in the appendix of the paper. So I mean, we can also maybe I can do the conclusion, and afterwards I can also
let's do that.
Go in the appendix of the paper and show the results there. Yes, I mean, conclusion, you know, so we propose this flow annealed importance sampling bootstrap approach, which is like a training algorithm for normalizing flows, which minimizes this alpha divergence at alpha equals to 2, and by using like several tricks such as, you know, I need importance sampling, this bootstrap training idea, and the replay buffer. And most important thing is, of course, this training algorithm does not require samples from the target. It only requires the target density. It results in like very high effective sample size compared to other methods. And also, I mean, we were actually the first to like efficiently learn the Boltzmann distribution of Alanine dipeptide without using any MD samples, by using 100 times fewer target iterations. I mean, you know, learning it to some extent is possible with other objectives as well, but you really saw, I mean, the numbers were much worse if we use other objectives. So we were really with the first two, learn this distribution very well without the use of any MD samples. Yeah, I mean, for more details, you can feel free to have a look at a paper which is available in arXiv. By the way, the paper has also been accepted at ICLR, so we're also going to present it as a spotlight presentation, I think, at ICLR in beginning of May. Code is also publicly available with some examples, also a Google Colab example that you can play around with for this 2D mix of Gaussians. Yeah, and as an outlook, I mean, we definitely want to scale this approach up to larger system. I mean, Annealed dipeptide has proven already to be quite challenging, even in those simples, although it's a relatively small molecule. So hopefully we can go to even higher, larger molecules. And yeah, we also want to do what Hannes kind of touched upon in the beginning, to have like maybe one model to model the Boltzmann distribution of many molecules. But yeah, we also think that the method could be applied to other branches of physics or even machine learning as well. So for instance, currently I'm working with a master's student and she's applying this approach to particle physics. But yeah, I mean, other applications, even with other machine learning models such as diffusion models, are possible as well. Yeah, and want to thank all of you for your attention, and yeah, I'm very much looking forward to further discussions. Of course, I mean, Hannes, if you're interested in, we can have a look at results using different values of alpha, including the forward scale divergence.
Yeah, awesome. First, thank you. And maybe before we get into, yeah, you can probably already switch to the paper if you want, but we also have the question in the chat how the if there's any consideration of any thoughts about scaling it up to the bigger molecules, like what has to be considered there.
Yeah, so
Laurence, do you maybe want to elaborate?
Yeah, so there's kind of two key things. The first is that your flow needs to be able to work for like an arbitrary molecular graph. So it needs to be able to take in any molecule if you want to do a flow over lots of molecules. And then the other one is if you just want to apply this to a single molecule that has many more atoms. And there the key issue is that as you increase the size of the system, the variance of the annealed importance sampling weights increases. And we've thought about it a bit. So we actually have, I think in Appendix C, like a bit of analysis on this. And we kind of have like some derivations that show if you increase the number of intermediate annealed importance sampling distributions by the same factor as the dimensionality of your problem, that you can then achieve constant variance in the loss. So this would imply kind of linear scaling with the problem size. Yeah, so that's this plot here that Vincent has. So here what we show is if you estimate this alpha equals 2 divergence loss with samples from P, the log variance increases linearly, or the variance increases exponentially. But if we do our method and increase the AIS number of distributions by the same factor as the dimensionality of the problem, then the signal to noise ratio is kind of constant. So that looks hopeful for this, but we still need to actually run the experiments and see what happens.
Nice. Cool. Then I think like I maybe have some other questions, but
yeah, maybe to just close this case off with the different values of alpha, I think this should be here, right? So here this is basically alpha equals to 1 should be the forward scale divergence. And this is all like estimate using samples from the flow, all with like doing annealed importance sampling and everything. I think also using the replay buffer, if I'm not mistaken. And you see, I mean, with using the forward Kerr divergence, you know, you're slightly better than if you use like those smaller values of alpha, which also are kind of more mode seeking. But still, I mean, the effective sample size is pretty poor. If you do 1.5, which is a bit closer towards 2, but not, but also a bit far away from forward Kerr divergence, you already get better. But really, the optimal case seems to be 2, right? I mean, effective sample size, okay, for the experiments that we did, seems to be even similarly high, or maybe even higher at alpha equals to 3, but then like the other metrics, they have their peak at alpha equals to 2.
Okay, well, this is great. Yeah, I'm very surprised, or this is really interesting that the alpha diverge, or the alpha equals 2 divergence also makes such a big difference to the forward scale.
Yeah, I think we think it's really due to the fact that minimizing the alpha divergence alpha equals to 2 also minimizes the variance of the importance weights. And then whenever we want to do this reweighting, of course, this is important, right? I mean, then of course we are better. And also, I mean, it also makes sense that it's better for training, right? Because I mean, during training, we also use our importance weights. But if we don't train in such a way that we minimize the variance might still be high, which is why we cannot train efficiently. So we cannot estimate our objective well. And this is why it doesn't work that well for the forward Kerr divergence.
Yeah. I have to say, this might be my my favorite iClear paper right now.
Awesome.
But we'll see. There will be many more contenders for that spot. So okay, cool. But then maybe thanks first of all. And yeah, no, before you get to some last words, do you know this paper right here? Share. Designing loss for data-free training of normalizing flows.
Yeah, I know it. Indeed, it's so we had a look at this. Like there are like a few things which we thought are a bit strange in this paper. I mean, so basically the idea there, just to summarize for everyone who is not familiar with this paper, the idea there is they basically tried to also I mean, as the title says, they also want to design like loss functions which ideally allows us to learn Boltzmann distributions without a lot of MD samples. However, what they're doing is still that they pre-train their flow with MD samples, and then they do fine-tuning using this objective that they introduce. But if you scroll down maybe a bit to this resulting figures, I think they also have results for Alanine dipeptide.
No, they have Alanine.
Yeah, I mean, this is it's the same name for the different name for the same molecule.
What,
so,
really?
Yeah,
I thought that's the case, and then yesterday I googled it and was really sure that it's not the same.
I think it's at least what we are talking. I mean, it's a bit difficult, right? Some people associate alanine dipeptide with like a molecule which really contains like 2 alanine amino acids, which is not like what we interpret it as. So what we actually mean is d-alanine. Yeah, this is the molecule we're considering, and d-alanine, I mean, it's the same. But some people use alanine dipeptide like the same name for like a different molecule.
But look at this. It's not the same. How do I find it now? No. Like this is not the same as the right?
Yeah, but d-alanine, this is I mean, this is the molecule this is shown here is not the molecule that I think d-alanine is sometimes also used for like a different thing. This is just 2 alanine amino acids connected to each other. But if you click back in the paper,
where do I find the paper? Here.
I mean, this is right. I mean, this is
yes.
This is alanine dipeptide. So, I mean, this is the same molecule that we considered. Maybe they used the wrong name or we used the wrong name, but I mean, if like the molecule that is depicted there is the molecule they trained on, it's the same that we used.
Yeah.
Yeah, this is
Same.
yeah, same. Yeah, and the thing is, yeah, so they basically, you know, they did pre-training on the so can you zoom out a bit? So they did pre-training, yeah, they did pre-training on the MD samples, which are shown in this, yeah, which is this orange graph, and then they did this refinement using their special laws that they introduced. And you see, I mean, on the in this right plot and the green plot, this is like the fine-tuned version. And I mean, to me, it looks that this mode on the right is even a bit worse resolved than before. And the problem is, I mean, they don't really have quantitative comparisons, so therefore they have no like numbers to back up their claim that they improve using fine-tuning. And when just looking at the pictures, it looks as if the results are basically worse than with fine-tuning than before fine-tuning. Then so therefore, yeah, I'm a bit skeptical about this paper in this regard.
Yeah, but it's very I think very educational, the paper, very instructive. So I still highly recommend reading it.
Yeah.
But how does their objective compare against yours, right? Because here we also have this this ratio, but they, yeah, how does this compare against your objective?
Yeah, so let me, I mean, they basically directly try to compute like the variance of this. But I think, yeah, so basically, yeah, they try to directly optimize the variance of this objective, which is like the log importance weights. I mean, I mean, there's this kind of similar, right? I mean, our objective is minimizing the variance of the importance weights. They tried to directly minimize the variance of the log importance weights. It's not exactly the same. And I think, as far as I remember, they also used some approximations to then come up with the final objective that they're using. While, I mean, ours is basically directly optimizing the objective using yeah, we can do this because we sample from this distribution p squared over q using innate importance sampling, while D8 I think needs an approximation for their objectives.
Also, are they sampling from?
Sort of the thing is that in your you additionally have a step where you change the samples that you get from your Boltzmann generators, and you don't just use these samples with reweighting. Is that correct?
Yeah, exactly.
So I guess there's like there's like two tricks you can do. You can play a lot with the loss, assuming samples from the flow, or you can also try to get better samples.
I hope you found the paper as fascinating as I did, with the Boltzmann generator like this for alanine dipeptide so far, but maybe in the future for really big molecular systems. And then we have achieved this dream of just being able to get samples of a molecular system instead of having to do molecular dynamics to get those samples. But if you want to have or join future exciting sessions like this, then feel free to do so with all of the information down in the description. See you next week, maybe.